about the worksheet from yesterday on Kepler's 3 laws. So if you look at kind of the history of science and big ideas that like fundamentally shifted how science and philosophy was done, Kepler's laws would rank up there. So again, you kind of have to understand the sequence. So the early Greeks said, and based upon observations and based upon the Bible, you had a geocentric solar system. Everything revolved around us. It made us feel good, okay? We watch the sun, it goes up over our head. We watch the moon, it rises, it goes over the head. The moon and based upon pure observations, the moon and the sun both take the same path across the sky, okay? You can't tell the difference between the two of them. But one of the things they struggled with is something called retrograde motion. So retro means like going back in time. So if you wear like retro clothes or if you listen to retro music, you listen to something that's back in time. And what they observed with the planets is that all of the planets undergo what's called retrograde motion. So like if you're familiar with like the constellation Orion, for example, okay? Because you have the belt of Orion, it's 3 stars. It's very easy to see, especially in the wintertime. And what they would observe is that over the period of time, Mars would, and this isn't within one night, this is like over months of time. Mars would appear to drift like to the left of the belt of Orion. And then about every 2 years, it would start to move backwards, okay? Now, I don't want you to think it moves backwards in the night sky, okay? It still rises in the east, it still sets in the west. That's the same path. But it starts to drift backwards relative to these stars, because that's the only way that you can judge the position. So it would drift backwards for a little bit, usually for about 3 or 4 months, and then it would stop, and then it would start going forward again, okay? So if you ever hear, and if you read your horoscopes, God forbid, it'll say, oh, like Mars or Venus or something is in retrograde motion. It's just talking about the motion relative to the stars. So when you had a Earth-centered solar system, and they said, okay, here's the Earth, and here's Mars, and it's going around us, and they would have what they call these little epicycles, where Mars would go in this direction, and then it would get pulled out of that orbit and have its own little separate orbit, because this is how you could explain how Mars was drifting backwards, okay? And then it would hit this point, and then it would start to go forward again. So if you looked at the early models of the solar system, when it was geocentric, you had all of these planets with all of these epicycles, okay? So this is before Isaac Newton and the laws of motion and everything else like this. But it was really, really complicated. Now it worked, okay? The epicycle model worked. You could predict when Mars was going to go through retrograde motion. It worked fabulously because Tycho Brahe had all of this data. But it just wasn't elegant. So Kepler comes along and he says, number one, he bought into the Copernican system where you have a sun-centered. You still had to be able to explain the retrograde motion. You still had to explain how that happened. So what happens in this explanation is that here's the sun, okay, and here's the path of the Earth, and here's the path of Mars. So what happens is because Earth is going faster than Mars is, what happens is that it's like a racetrack. So Matt would be on the inside track, and Kara would be on the outside track. So what would happen is that because Matt's on the inside track and he doesn't have as far to run, he's going to pass Kara on the inside. And when he does, you change the perspective. You change this perspective of how Matt is viewing Kara. So Kara doesn't actually go backwards, but it appears that way because Matt is passing her on the inside. So that was one of the key things that Kepler's model had to be able to do, was how do you explain this retrograde motion? And he says, oh, it just happens because it passes it on the inside. So, again, it's hard to convey the difficulty and the genius of what Kepler did, because he's trying to judge the position of Mars without any fixed point. So if you've ever gone out at the night sky and looked at any of the planets through a telescope or whatever, you can't look at it and go, oh, okay, well, clearly Mars is 2.2 astronomical units away. I got that. It isn't like it's a golf thing where you have like a rangefinder where you can like shoot a laser at Mars and have it bounce back. So Kepler was on a spinning rock, a rock that was tilted on its axis. Earth itself is in a little bit of an elliptical orbit. You're trying to judge the position of Mars relative to all these background stars. And he's got to sift through like 20 years worth of data that he stole from Tycho Brahe, the gold-nosed guy. So there's a whole bunch of things that were stacked against Kepler. But in his heart, he goes, look, I'm on a mission from God. This is why I was put on this earth. So Kepler hated this model with the epicycles because it was just so convoluted and so complicated. So Kepler thought there should be a very elegant way to express this. So the first thing we talked about yesterday, he came up with the law of ellipses. Ellipses have two foci. One foci is going to be where our star is, okay, our sun, and the other one is some point out in space, okay, which again was created a controversy because everybody thought the planet should move in perfect circles because that's the perfect geometric shape, and this is the realm of God, and God should have made a perfect circle, and he didn't. He kind of made an ellipse. It's like, oh, seriously. Okay, so that's the first law. Second law is that we sweep out equal areas in equal times, and this is the whole point of the lab that you're going to do today. So if you drew a line, and this is Kara if you hold up that one that you already did, okay? So what Kara has is what you're going to end up looking at. So what we're going to do, Kara, ahead of the game, shaded in these areas, okay? And what you're going to do is you're going to pick your own areas and you're going to see if that matches up. Now the only way this works, and this is what you have to remember out of Kepler's second law, is that when you have the planet being closer, okay, when you decrease the radius, you increase the velocity. The closer you are, the faster you go. When you go out here, you increase the radius, but you decrease the velocity, okay? So that's going to be the second law, and that's going to be what's most important. Okay, so let me hand out the actual lab. So we're going to go through this. We're just going to just kind of piecemeal this together. Okay. So for those of you in the studio audience, so you've got your map, okay? And here's the first one. Looking at your graph, does the orbit support Kepler's first law? So when you look at your points, does it look like an ellipse? Yes. So that's all you have to say. Yes, it looks like an ellipse. Now, if it had been a circle, plotting your points would have been a lot simpler. All you would have had to have done is take a compass, put the point in the center, and draw a circle around the edge. Would have been much simpler, okay? But it's not. It's an elliptical orbit. Okay, now, here's what we're going to do next. The first 10-day period we're going to do together so that everybody knows what's going on. So what we're going to do is that we're going to figure out the area between December 20th and December 30th. So you have your data. So we're going to look at what's going to happen between December 20th and December 30th. Okay. So Matt, what's the radius, or What are you giving? What's the radius on December 20th?
0.309,
And what is it at December 30th?
0.327,
Okay? And what's the degree on December 20th? Where is it?
65 degrees,
And on December 30th, it's at
126 degrees.
126 degrees. Okay. So if you look on your map, okay, here's your circle. So this is where you're going to get these lines that Kara has on hers. Okay? So you've got all these concentric lines. So on December 20th, you're at 65 degrees. So you're going to draw a line from the center of the circle, and 65 degrees is going to be like something like this. Okay? So here you are on 12/20. And then you're going to come over here on December 30th, which is 126. Okay? So here you are on December 30th. Now, and you're going to shade this in. If you want to just use colored pencils, I've got colored pencils over there. And if you just want to shade it in with your normal pencil, that's cool. Now, Kara, hold that up again. So when you shade this in, go only to the edge of the orbit that you drew. Don't go all the way out to the edge of the graph, okay? Just go to the edge of the circle that you have, okay? So what we're going to do is that we're going to find this area that's swept out between December 20th and December 30th. So to do that, there's a couple of ways you can do this. One's pretty complicated and one's pretty simple. We're going to go with the simple way. So what we're going to do is we're going to find the average radius between 0.309 and 0.327. You don't have to go through and add together all 10 radii and then divide by 10. We're just going to make this simple. So Matt, take 0.309. We're just going to find the average of these two numbers. So Matt, take 0.309, add that to 0.327, and divide that by 2.
0.318.
What?
318.
Okay, 0.318 astronomical units. So what we're going to do is that we're going to use this formula that I have on your sheet. So what this is going to do, this is on your lab. So it's theta over 360 equals pi r squared. So what the theta tells you is what portion of a circle, because remember there's 360 degrees in a circle. So this tells us how much of the circle that we're looking at. Okay? So on December 20th, we were at 65 degrees. And on December 30th, we were at 126 degrees. So Matt, take 65 minus 126.
Negative 61.
Okay, just call it 61 degrees. Okay? So here's what we're going to do. To find the area swept out from December 20th to December 30th. We're going to take 61 degrees, because that's how many degrees it moves through, is 61 degrees. We're going to divide that by 360, and then we're going to multiply that by pi times our average radius squared. Okay? So Matt, take 61, divide it by 360, multiply that by pi, multiply by that by 0.318 squared.
0.054.
So give that to me in scientific notation with 3 significant digits.
5.38 times 10 to the second.
Times 10 to the negative second?
Negative second. Yeah.
Negative what?
Negative second.
Okay, we're good. Now, what units do I have? What's the only thing on there that has any units? The radius. And that's measured in? Yeah, so our units are AU squared. So, on your lab, okay, Here, you determine the area swept out between December 20th and December 30th. So your theta is 61 degrees. The average radius is 0.318. And the area swept out is 5.38 times 10 to the negative second AU squared. Now, here's what you're going to do, okay? You're going to go through and you're going to pick your own 10-day periods, okay? I would suggest maybe you get something down in this region and maybe something over here so that you kind of get this thing spread out. Now, what I would suggest is that don't cross over like 0 degrees, okay? You can do it, but calculating the angle gets a little bit tricky, okay? So I put something down over here, something down over here. Now, there's a couple of things because everybody's 10-day periods are going to be different, okay? So there's a couple of things. Number one, you're going to write it on here. So let's say that you picked October 1st to October 11th, whatever it is, whatever your 10-day period is. So you're going to write down the dates here. Then you're going to say, oh, it's at so many degrees minus so many degrees, and that's going to get you your theta. And then you're going to write down R1 plus R2 and then take the average of those two. Now, the other thing that I want you to do is on the page that has all of your data, okay, that has all the dates, right? Whichever 10-day period that you pick, I want you to come in there and box that out. So that way, if I'm trying to figure out what you did, maybe you wrote down a number wrong. That way, it makes it easy for me to see what those dates are. So you're going to pick 2 additional 10-day periods. So when you get done, I should see 3 boxes on the data table, whichever the first one we did together, December 20th to December 30th. So that's going to be the first one that you're going to shade in. Then you're going to have the other ones off of that data table that has all the information. Then you're going to have 3 different shaded areas on the map itself. Okay? So, get that done. Okay. So, on page 2, and hopefully all of your areas are something around like 5 times 10 to the minus second AU squared. That your areas should be something around there. If they're not, you've done something wrong. Okay? So this is what I should be able to see at this point. You should have your graph, and I should be able to clearly see which 10-day periods that you picked. Good? Shaded in with a pencil. And again, that's just so when I go to grade these, I can visually see what those 10-day periods are. So what you're going to do on top of page 2, now that you have those 3 areas, now you're going to add, and I don't need to see this, I know you all can add together numbers and divide by 3. So you're going to find the average of those 3 days, or those three 10-day periods. You're going to get that average. And let's say, I'm just going to make up a number, let's say that your average is 5.1 times 10 to the minus second AU squared. That's whatever your average is, I just made up a number. Okay? So what we're going to do is we're going to compare each measurement to that average to see how much variance that we have. Okay? So if you look on that, so let's say that that first area that everybody has is 5.38 times 10 to the minus second. So if this is your average, okay, if that's your average, then you're going to take 5.1 times 10 to the minus second, or whatever your average is, okay, whatever your average is, minus that first area, 5.38 times 10 to the minus second. Then you're going to divide that by 5.1 times 10 to the minus second. Multiply that by 100, and that's an absolute value, okay? Now in statistics, this calculation becomes a lot more complicated because you do like a standard deviation. So you subtract it, and then you square it, and then you find the sum, and you divide by 2, and you take the square root of all of that. Or we're just going to make it a little bit more simple. So, and again, everybody's numbers is different. So here's the short version of what you're going to do. You're going to take the average minus each trial divided by the average times 100. Okay? That's the short version, right? So for that first trial, this is going to be the same for everybody, because everybody's first 10-day period was 5.38 times 10 to the minus second. But everybody's averages is going to be different. So the only thing that I can grade you on is the process. So what I want to see off to the side is going to be your average minus a trial divided by your average times 100. So give you a little bit of time, get that done. Okay, so hopefully everybody's got that part done. So now now you get to question number 10. Do your results validate Kepler's second law? So a second law says that you're going to sweep out equal areas in equal times. So assuming that your percentages are pretty small, like Shivani's was around 2 or 3%, hey, that supports it, okay? So there you go. Now, so we're going to do number 11 together. So make sure we got this one right. So somebody go through that data on number 11 and find the smallest radius for the entire data set.
December 22nd.
Huh?
December 22nd.
But what's the actual
307.
number? Like the actual radius?
0.307.
0.307. Okay? And that occurred when? December 22nd?
Yep.
Now, what's the absolute largest radius that you have?
November 8th, which is 0.467.
And that's November 8th? Okay. So, and instead of going through and adding together all of these numbers and dividing by the total value, we're just going to make this simple, okay? We're just going to find the average radius between the smallest radius and the largest radius, okay? So, Matt, or somebody, take 0.307, add that to 0.467, and then divide that by 2.
0.387 is what I got.
0.387? Okay. Okay, so everybody's going to have the same answer to number 11, and that's 0.387. So what we're saying is that on average, okay, on average, this is how far Mercury is from the sun. Okay? There you go. Now, on number 12, there's some different ways that you can do number 12. I'll leave it up to you. But fundamentally, you're going to use Kepler's third law. So you're going to have 4 variables. You can have the period of Mercury, the period of the Earth, the radius of Mercury, and the radius of the Earth. Okay? Those are your 4 variables because you have Kepler's third law, right? So what's on your equation sheet, okay, if you look on your big dog equation sheet, you would write this as the period of Mercury squared times the radius of the Earth cubed is going to equal the period of the Earth squared times the radius of Mercury cubed. Now, let's backtrack. I completely forgot about the assignment. We didn't go over that because I'm out. So let's back up. Does anybody have any questions on that sheet from yesterday? Anything at all you want me to go over? Let me give you some hints, okay? Your answer to number 8 should be something close to your age. okay? Your smallest answer is going to be number 7, which is the orbital radius of Venus, okay? And when you get to number 9, here's the deal. Here's the Earth, here's the Moon, here's the satellite, okay? So, you know that the distance is half that of the Moon's, okay? So this is 0.5, and you're going to make that 1. The other option that you could do is you could let this be a distance of 1, and you could let the distance to the Moon have a period or distance of 2, okay? So you could either go 1 and 2, or 1 and then make that a half. But again, you have 4 variables. So you've got the period of the satellite squared times the radius of the Moon cubed is going to equal the period of the Moon squared times the radius of the satellite cubed. What you don't know is the period of the satellite. So you got to take whatever. Now, what I would do personally, and if you were Kepler, you would do the same thing. What would you let the period of the Moon be? Huh? 1. I'm just going to let that be 1 lunar orbit. You have the radius of the satellite, which is going to be 0.5. And then you've got the radius of the Moon, which is going to be 1. So the only thing you don't know is the period of this satellite. So take this, divide it by the radius of the Moon cubed, boom, take the square root of that. So here's how I want this answer. Let's say it works out to be 0.25. It's not, but let's say it is, okay? But you know it's got to be a decimal. So here's how you're going to give that answer on that last question. You're going to say, if your answer was 0.25, and it's not, but let's just say it was, you would say, oh, the period of the satellite is 0.25 times the period of the Moon. So you're just going to insert whatever your answer is. So your answer is going to be 0 point something times the period of the Moon, because that's how you're asked to give your answer. Now, here's the beauty of it, is that once you actually knew the period of the Moon, then you could multiply that decimal by the period of the Moon, and then you would have the period of the satellite. Okay? That's one of the things that you could do. Okay? And I cannot emphasize this enough. This only works, and it works beautifully, but it only works for objects that orbit the same center. And once we get into Newton's laws, you'll see why it works that way. Okay? But you have to be orbiting the same center. Now, if you look at what Kepler did, and this is going to play out into what we're going to talk about next. Kepler never tried to explain the mechanism because he didn't have a very good understanding of gravity. Newton hadn't published his works at this point, okay? So there was no way to calculate the gravitational field. Kepler basically said, hey, here's the story. This is what's happening. I'm going to leave it to someone else to figure out, okay? So now, if God wanted to make life simpler for Kepler, what would have been the easiest ratio that could have existed between the period and the orbital radius?
1-to-1.
Yeah, a 1-to-1 ratio. If it had worked out to be a 1-to-1 ratio, like in this situation, if the period of the satellite was half that of the Moon's, the rate then, if that was the case, then the period of the satellite would be half that of the Moon's. Okay? That would have been the simplest ratio. But even then, it wasn't bad. It was squared and cubed. It wasn't like it was to the 15th and to the 23rd, which would have been horrible. Okay, and especially daunting if you consider that he did this without the aid of any computer program, anything like that. He did these computations by hand and was able to trace this out. So, if you're ever searching for a cool research paper, write one on Johannes Kepler, because what he was able to pull off is pretty stunning. And if you're not, pull up Tycho Brahe, because of the fact just because he has his gold nose, and that makes it worth it. Okay. All right. So no questions on that sheet? We're good? Going once, going twice, sold? Okay. So back to the lab. Sorry. Kind of had to jump around a little bit. All right. So what you're going to do back on number 12 And here's the decision that you have to make, okay? And because of the fact that I don't care, it's the only time I'm ever going to tell you this in this class, I don't care what the units of period is in, I don't care what the units of radius is in. They just have to be the same because it's a ratio, okay? So, if you let the period of the Earth be 365 days, then that means when you get this answer for the period of Mercury, that's going to be in days, okay? If you let the period of the Earth be 1 year, that means the period of Mercury is going to be in years, okay? Because it's a ratio, it doesn't matter. But because of the fact that the period of Mercury is so fast, I'd work this. So, you got the period of the Earth, 365 days. Radius of the Earth is going to be what? 1 astronomical unit. You just found the radius of the Mercury. Okay, that's what we just found, which was the average of those two values. The only thing you don't know is the period of Mercury. So you're going to do that. Now, when you get down to question number 13, okay, let me explain how I want question number 13 done. On October 1st, where is Mercury? What's the degree of Mercury on October 1st?
114.
What'd you say? 114 degrees. So you're going to figure out how many days it takes to go from 114 degrees, okay, all the way back to 114 degrees. Okay, so you have all of this data, right? Now, you're going to count the number of days. So, and this will make sense. You don't count the same day twice. Even though October has 31 days in it, we're only going to count that as 30, so that way we don't count the day when it gets back to that same point. Okay? So, you're going to have 30 days in October, obviously all of November, and then how many days in December is it going to take to get back to that point? So that's going to be that answer to number 13. Okay? So, make all that happen.
That'll tell you what's cancel out. So like right now, t squared, that's equal to 365 days squared.
Okay. So, what you should see is that the counted days and the calculated days should be around 90. Okay? That's an ish, but they should be around 90. Okay?
Squared.
Not exact, it's going to be something around them. So, what all that we did is that we said, okay, out of this calculation, here's the predicted value of the period of Mercury. And then we're actually going to count it and go, oh, this is what we actually got. Okay? Like I said, both those answers should be around 90. So now we're going to transition from what Kepler did into the Newtonian explanation of why it works. So on the top of page 3, number 1, okay, so here's what you're going to do. You're going to go to your map. Here's the next thing that you need to do. You're going to do 4 things, okay? Keeping in mind that Mercury, like everything in our universe, is going around counterclockwise, okay? Because they think everything's moving counterclockwise is because when our solar system formed, it was just like this spinning mass of particles. It was like a pinwheel, and then things began to clump together, and as they clumped together, they created more of a gravitational field, and they pulled more and more stuff together. Okay, so when you look at what's going to happen here, you're going to need to do 4 things. You need to find the single point when Mercury is closest to the sun, and you're going to label that with like the highest velocity. So let's say that you think when Mercury is closest to the sun, it's going to be right there. So you're going to pick that point, and you're going to say, okay, this is going to be my greatest velocity, and then maybe draw like a little arrow that says, okay, at that single point in time, this is when Mercury is going fastest. So is it going to be going fastest when it's closest or when it's furthest away?
Closest.
When it's closest, okay? And what you'll see later on, that's a function of energy. It has its most kinetic energy because it has its smallest potential energy. Now, when is Mercury going to be going its absolute slowest?
It's farthest away.
So you're going to go through and you're going to find that single point, wherever that is on here, and you're going to go, okay, that's the point when Mercury is going slowest. So you're going to find that date when Mercury is going as far away as it can possibly be. And you're going to go, okay, that's when it's going to have its smallest velocity, okay, draw an arrow to that point, okay? So you're going to have one fixed point when it's going fastest, and you're going to have one fixed point where it's going slowest. Now, the next thing you want to do is you want to label from there when Mercury is speeding up and when Mercury is slowing down. Okay? Well, since Mercury is going in a counterclockwise path, if it's going fastest here and it's going slowest here, is it slowing down or speeding up during this part of it? Shivani?
It's slowing down because it's the fastest there and the slowest there.
Beautiful. So you could like come out here, draw an arrow. If you wanted to, you could draw like a line here, and then connect that. If you want to get fancy and like shade in this area out here and go, oh, this is when it's slowing down, I don't care, okay? So then, by your next thought process, if it's slowing down to here, once it gets past that point, then what's it going to start to do?
Speed up.
Then it's going to start to speed up, okay? And again, you can just draw an arrow out here to this point and go, okay, hey, this is when it's speeding up. You want to, that's however fancy you want to get. Main thing is that both you and I should be able to look at your graph and know exactly when it's slowing down and exactly when it's, the region when it's slowing down, the region when it's speeding up, and the exact point when it is going fastest and when it's going slowest. So make that happen. All right, so now that we know when Mercury is going fastest, when it's going slowest, slowing down, speeding up. So now we're going to use that information to segue into Isaac Newton. So Isaac Newton did his work in the late 1600s, well after Kepler had died. So if, let's just say, hypothetically, and obviously I hope this never happens, but let's say all of scientific knowledge is wiped out and we have to start over from scratch, okay? And if you said, okay, you get to pick one equation to start over with, this would certainly be on my top 5. So let me explain the ramifications of this equation. Okay, so first off, this is going to be your gravitational force between any two objects that have mass. This big G is called the universal gravitational constant. This number is on the top left square of your big dog equation sheet. Okay, so don't memorize it, it's there. Okay? And it has a numeric value of 6.67 times 10 to the minus 11th newtons meter squared over kilograms squared. Okay? Now, later on you'll see why these units work out like they do. They look kind of convoluted, but there's an actual simplicity in the elements. Now, we're going to be using this number a lot, 6.67 times 10 to the negative 11. What I would recommend that you all do on this unit, I would store this number in a memory cell in your calculator. But when you do this, okay, don't type in times 10 because it's going to screw up your order of operations. You should have a 6.67 and then there should be like an EE key if it's a Texas Instrument calculator. There should be like 6.67 EE negative 11. And then you should have a button on your calculator that says like store, like STO or something like that. And then you could store it and assign it different variables. I most of your TIs, you can assign it like the whole alphabet. I would assign this as being the value of G. Now, you don't have to do that. If you want to punch in 6.67 e to the negative 11th every time you use this number, hey, fine, knock yourself out, okay? But if you store it, that's going to make life a lot simpler, okay? That's just up to you. If you don't know how to store something on your calculator, we can figure that out. Okay, now here's the significance of this. So, if I want to calculate the gravitational force between any two objects, okay, I mean between any two objects, I only need 3 bits of information. I need the mass of the two objects and how far apart they are. So here's the philosophical ramifications of this equation. Is that you all have mass, okay? You do. What that means is that you are attracted gravitationally to this Earth that we're on, obviously, okay? You're attracted to that solar panel in the back. You're attracted to the moon. You're attracted to the sun. You're attracted to Jupiter, everything. You are gravitationally attracted to the most distant electron in the most distant part of our universe, okay? So the only way that you can be in true zero gravity, okay, and this is the ultimate freshman experience, the only way that you can be in zero gravity is if you are the only thing that exists in the universe. If there is anything else that has mass in the universe, you are going to be gravitationally attracted to it, okay? So you are attracted to every single bit of matter that exists in the universe, okay, no matter where it is. So what we're going to do is we're going to look at a simple calculation between Kara and that fire extinguisher. So we're going to calculate the gravitational attraction between Kara and that fire extinguisher, okay? So here's Kara, and let's say that Kara has a mass of 50 kilograms. And here's the fire extinguisher. And let's say that that has a mass of 2 kilograms. And let's say that they are about 5 meters apart. Okay? So Kara's here. The fire extinguisher hanging up on the wall is over there. Kara has a mass of 50 kilograms. The fire extinguisher has a mass of 2 kilograms. I want to calculate the gravitational attraction between Kara and that fire extinguisher. Okay? So, Matthew, if you would, we're going to take 6.67 times 10 to the minus 11th newtons meters squared over kilograms squared times the mass of Kara, 50 kilograms, times the mass of the fire extinguisher, 2 kilograms. And then we're going to divide that by 5 meters squared. Okay? So basically it's 6.67 times 10 to the minus 11th times 100 divided by 25.
2.67 e to the negative 10.
2.67 times 10 to the minus 10th.
10.
Okay. Now, look at what happens to the units. Okay? Look at what happens to the units. I take kilograms times kilograms. What do I get when I take kilograms times kilograms?
Kilograms squared.
Kilograms squared. Okay, so the kilograms are going to cancel out. Down here I'm going to square meters, so I'm going to get meters squared, so that's going to drop out those meters squared, right? And the only thing I have left with is newtons. So that's the gravitational force that exists between Kara and the fire extinguisher. We'll stop here. We'll finish up those tomorrow. So we'll finish up the lab. No, not even tomorrow. We won't meet tomorrow. We'll finish this up on Monday. Okay? So make sure that I get that Kepler's assignment if you haven't turned that in. And enjoy kind of a 3-day weekend from physics.
So no homework?